Have you ever written code like this? It looks clean, modern, and totally correct. Your peers will even comment during code review. Nice. This is very idiomatic C++. But once it goes live, the performance slows down inexplicably. In today's video, I'm not going to talk about any fancy tricks, and I'm not against clean code either. What I want to discuss is a very practical yet rarely openly addressed issue in C++ engineering. The most expensive code in C++ is often not the complicated kind, but the code that looks extremely clean. In many programming languages, Python, Java, Go, for example, writing cleaner code usually only affects readability and rarely impacts the performance model directly. Python has the GIL to fall back on. Java features JIT dynamic optimization, and Go's runtime shields you from most low-level details. But C++ is different. Its design philosophy is zero overhead abstraction. It's zero overhead, not no overhead. What this means is that the cost of abstraction must be actively controlled by you, not hidden by the language itself. In C++, almost every abstraction you write maps directly to specific machine behaviors. Is there an indirect call? Any extra memory access? Can it be inlined? Will it trash the cache? The catch is that these costs are usually well hidden by elegant syntactic sugar. Let me walk you through a few real-world examples that almost every C++ project has fallen victim to. First, let's look at something everyone is familiar with: std function. From an interface design perspective, it's absolutely perfect. It decouples components, unifies types, supports substitution, and is easily testable. Whether you're binding function pointers, lambda expressions, or member functions, it integrates seamlessly. But from a performance standpoint, what is std function essentially? It's type erasure. It needs to store a copy of the function object at runtime and use virtual functions or function pointers to forward the call. What does this imply? First, it usually involves an indirect call executed via table or function pointer jumps. Second, it's almost impossible to inline. Compilers can't predict the actual target function to be called in advance. Furthermore, in some cases, it may even trigger heap allocation. If the stored function object exceeds the SBO small buffer optimization threshold, it will allocate space on the heap. In cold paths, like configuration loading or user interaction callbacks, these costs are negligible. But if you put it in a tight loop, high-frequency callbacks, or core data processing pipelines, what you get is not a clean abstraction, but a steady, ongoing performance tax. I'm not saying you should never use std function. What I mean is you must be clear. You're using a runtime polymorphism tool to solve a problem that could have been resolved at compile time. So are there alternatives? Absolutely. If the call target can be determined at compile time, using template functions or std invoke paired with function pointers delivers almost the same performance as direct calls. If runtime polymorphism is truly necessary, you can also consider virtual functions. While they still involve indirect calls, they don't carry the extra overhead of type erasure. Let's move on to an even more common scenario. Is there anything wrong with this code? Syntactically, it's completely fine. And it's super clean, no extra symbols, crystal clear at a glance. But there's a dangerously hidden detail here. AutoX is a value copy. If vector stores large objects, resource holding objects, or cache sensitive structures, this line of code you just wrote will silently perform a copy in every loop iteration. The copy constructor gets called, memory is allocated repeatedly, and the cache is flushed constantly. Worse still, it's completely inconspicuous. No new, no delete, no malloc, not even an extra function call. Before you run a profiler, almost no one would suspect this single line of code. The actually correct, albeit slightly less elegant version looks like this. This is the reality of C++. The safest code is often not the first line that comes naturally to mind. Many developers swear by this rule of thumb. Keep functions small, logic clear, and responsibilities single. From an engineering management perspective, this is totally valid. It facilitates maintenance, testing, and collaborative work among teams. But in C++, this rule has a hidden prerequisite. The function must be inlineable. Otherwise, what happens? Every small function becomes an optimization boundary. The compiler can't reorder instructions across function boundaries, eliminate intermediate variables, merge memory accesses, or even perform loop unrolling. This is especially true in three scenarios: header and CPP separation, LTO not enabled, and multi-compilation unit projects. Let me give you an example. Suppose you split a simple math calculation into two small functions, add and multiply. In debug mode, the performance is roughly the same as the non-split version. But in release mode, the non-split code can be optimized by the compiler into a single machine instruction. Meanwhile, the split version retains the overhead of function calls. Although the cost of a single call is only a few nanoseconds, when called millions of times in a loop, the gap becomes extremely significant. This isn't a problem with coding style, it's about whether you understand how compilers work. The right approach is prioritize making functions inlineable. For example, define them in headers or use the inline keyword. If splitting is unavoidable, make sure to enable LTO so the compiler can see all function implementations during linking. Also, avoid splitting overly fine-grained functions in hot paths. STD shared pointer is another classic example. On the surface, it offers automatic lifetime management, clear semantics, and fewer memory errors. Especially in multi-threaded scenarios, you don't have to manually manage pointer ownership. It's incredibly convenient. But where does its real cost lie? Not in construction, not in destruction, not even in memory allocation, but in the atomic operations of reference counting. The reference count of STD shared pointer is thread safe. This means every copy, assignment, and destruction triggers an atomic increment or decrement operation. The problem with atomic operations is twofold. First, they block the CPU pipeline and prohibit instruction reordering. More critically, in multi-threaded environments, when multiple threads manipulate the reference count of the same STD shared pointer simultaneously, it leads to cache line contention and false sharing. CPU caches are allocated in units of cache lines. If the reference count shares the same cache line with other frequently accessed data, a modification to the reference count by one thread will invalidate the cache of other threads, forcing them to reload data from main memory. This overhead is even greater than the atomic operation itself. To make matters worse, the cost of STD shared _PTR is hard to capture with profilers. Profiling tools typically show the time spent on function calls and memory allocations, but the time consumed by atomic operations and cache invalidations is often categorized as unknown overhead, making it difficult to pinpoint. I'm not saying STD shared pointer is bad. What I mean is you need to know when to use it. If shared ownership is truly required, STD shared pointer is the best choice. But if you only need single ownership, for example, creating an object inside a function and returning it to the caller, STD unique pointer is more than sufficient. In hot paths, even if shared ownership is necessary, you can consider alternative solutions, like object pools or manual reference count management, provided thread safety is guaranteed. At this point, I want to emphasize one thing. I'm not saying modern C++ is wrong, nor am I advocating against abstraction or claiming dirty code is faster. The real issue is this. In C++, abstraction comes with a price tag, and it's the responsibility of engineers to actively evaluate that cost. If you found this video helpful, chances are you've fallen into these traps before. Don't forget to like and subscribe so you won't miss future content. See you in the next video.